that, why 2 months, why didn't you?
Well, looks like we can officially start. Welcome back, everyone. So we had our first exam. Congratulations on getting through that, everyone. These exams can definitely be tricky in college algebra. But for our very first one, the average came out at 85.9%, which is really quite well for this class, I'd say. It's a two-way tie for the maximum grade at 99%. So congratulations to those folks who achieved that grade there. That's definitely not easy. Since, I mean, there's always tiny little subtleties on these kinds of exams that you just have to get used to doing these problems before you start to see them reliably. If you're not totally happy with your grade, there's a couple things you can do. One thing would be definitely improving your ALEKS grade right here is pretty massive because it's kind of double dipping. It's the same type of questions you're going to see on exams, and you can bring up your grade in that kind of way. I pushed the extension on all the chapter 3 sections to Tuesday of next week, since our current section is 2.4. Actually doesn't have any homework associated with it. It's just some topics we need to know about complex numbers before we get into chapter 4. So today's kind of a lighter day. Really, it's a good opportunity to get caught up and improve your grade. Also, another thing to mention about your exam is there's 2 scores on it. Your first score is a fraction out of the total possible points, which was 78. When you go to Moodle, your exam 1 score, it gets converted into a percentage. But your second score, called course score, is just your standing in the class as of today. I updated your ALEKS grade on Tuesday, so not completely updated, but very accurate. And here's how I computed it. 20% was your ALEKS grade. 10% is just the quizzes that have been due. And your exam 1 is weighted as a full-on 70%, which isn't fair, but it's just a best way to tell you about how you're doing in the class so far. At the end of the semester, exam 1 is going to be weighted far, far less. And so your grade has a huge opportunity to improve as well, based off that. Well, any questions, folks, about the course score, exam score issue or anything else? Okay, and typically when I pass back these exams, I typically put the solutions right here and ask the class if they have any questions. But for this exam, I did have a student which had an emergency to make up the exam later. And so I'm going to be posting the solutions probably next week so that you can check those out. And it's going to be a great opportunity to study for the final exam as well. In fact, what I would do if I was taking this class is definitely take your exam 1, put it somewhere safe, because once we go down here, it's a huge resource for studying on the final exam. There'll be other resources, but that's a great one. You'll have the solutions as well. So that's another way to get extra practice for the upcoming final exam. Well, that's my spiel after returning the exam. Any questions or comments at all, folks, at the moment? Okay. One last thing I want to mention is I do offer an extra credit opportunity. I don't have it down here. I forgot to include it. I'm just going to go to a different class. I usually do this in all of my classes. We're not doing statistics today, so no worries. I usually offer this extra credit opportunity, and I'll be doing that in this class as well. The way it works is, well, the motivation behind it is there should never be one exam that brings down your grade by a letter grade or more. And so if there was a rough exam that you didn't feel you were very happy with amongst exams 1, 2, and 3, everybody has an off day. Your final exam score, if it's higher, will replace your minimum grade amongst exams 1, 2, and 3. So that gives you an extra credit opportunity right there as well. Well, other questions or comments so far, folks? Okay, let's go back to the right Moodle page. I'll put that in writing in our own Moodle website. I'm just pretty much going to copy and paste it. So at the moment, we're in this section right here, complex numbers. Again, it's kind of a lighter section. For some reason or another, the math department didn't even create a ALEKS topic for this, so there's no homework based off it. But it's things that we're going to be looking at and doing in chapter 4. And so I wrote a quiz number 5, which is going to be based off those kind of topics. It's kind of a short quiz. They all of them kind of are. First one's not so bad. Second one is a little bit tougher, but it's really just foiling. And that's the nasty one. So our goal for today is to see how to calculate all these and to mostly discuss what is I when you say A plus BI. So that's how the quiz will go. Before we do any of those things, there was a comment last or about a week ago, I believe, about open and closed intervals on certain topics, where a function is increasing, where it's decreasing, and where it's constant. So I want to turn to a problem there for just a moment, and then we'll jump into section 2.4. Does that sound all right to everyone? All right, let's now go to Alex for, again, just a moment. I found it's not a good idea to log into here before class because they just logged me right out, and then I'm taking extra time to get back in. So this is a topic in section 3.3. And the one I want to take a look at is this one right here. I mentioned in class, when you give these kinds of answers, the typical thing you do is you always put open parentheses. This one's asking about strictly decreasing. And so the answer should be from here to here, going from 3 to 6. I would put that in parentheses, but what I've discovered in Alex is they take pretty much whatever you want, parentheses or brackets. That's a little bit odd. So I still think the most correct answer for this is, let's zoom in so we can all see the scale here. It's strictly decreasing when we go from, forgot this interval, -2 to 0. So if I put it in as a bracket, well, it's not the best way to say it because right at -2, that's a transition point. It went from constant to decreasing, around to -2 rather. And so the better answer really should have been like this, -2 to 0 to get that decreasing. And then from here, 3 to 6. Ordinarily, we put a union symbol here, but for one reason or another, they want this comma separated. So comma, 3 to 6. So that's how I would answer this kind of question. Does that make sense at the moment? Okay, so if I hit check, here it is, they say correct. But again, I discovered, I'm glad folks asked about this, they accept brackets as well. They really ought not have, but it is a really tiny, subtle technical issue there. And so when I graded exams about this kind of stuff, I didn't take off points either, since I mean, the homework is doing it that way. I can't expect you to do it differently on the exam. Let's try another because this isn't the one I was going for. I want, this is strictly increasing. And that's what I wanted here, constant. Determine the intervals on which the function is constant. Any volunteers for what the interval ought to be?
-6 to -4.
-6 to -4, absolutely. And then one more piece, that's kind of hard to see. Let me see if I can zoom in even more. Exactly, so comma, -2, -1. Then everywhere else, it's increasing. Here it transitions to decreasing. And so it's only constant in this region and in that region there. Let's check that out. They're happy with the answer. And again, that puts us in a weird, interesting conundrum because they are accepting brackets. The best practice is always use parentheses if they're talking about increasing, decreasing, or constant. But I'm not going to be nitpicky about that. That's just more something to be aware of in case maybe you're taking calculus and your next teacher is nitpicky about those ideas. It might come into play.
Could you use the union symbol for that as well, or just the comma?
Here, I wanted to use the union, but they didn't even provide it. So I was all confused there. And I read it and they said, make sure to separate each individual with a comma and use as few intervals as possible. So who knows why? Most of the problems, they want a union symbol, but here they asked for a comma. There's no rhyme or reason to that. Just a weird Alex issue, I'd say. Other questions so far? Okay, well, thanks for, I forgot who asked about that question. Thanks for asking that question. Let's now turn to our current section, 2.4. Again, the section is kind of a small review, get everyone on the same kind of page kind of section. And I started it off with this huge, huge blurb right here. This is actually stuff we've seen before to a certain extent. We have in the past wrote down a symbol that looked like this. We said that that's the set of all real numbers and an interval notation that goes from -infinity to positive infinity. And that's what's indicated right there. It's a really helpful shorthand for us, but there are loads of different kinds of shorthands. Let's zoom in this just a bit more. If you saw the symbol that looks like an N with a weird little thing in the middle, a double line, we're looking at the natural numbers or the counting numbers. And I put here the reason for existence. There's a need for counting stuff, not much to say there. This was our premier number system as human society for many hundreds, thousands of years. Then we came up with this system. Suddenly there's a need for zero as human society got more and more complicated. And the value is you couldn't solve that equation if you were just dealing with the counting numbers 1, 2, 3, and so on. You have to subtract 5 from both sides to get the number 0. So we extended the number system to the set of integers, z plus, positive integers. The z there, if you're curious, comes from the German word for number. I don't know what that word is, but it starts with z as much as I can tell you there. And so that's one of the reasons you see that indicated. So z plus means non-negative numbers. So starting at 0, complete the set and just call it z. Now we have all of the integers, positive, negative, and the 0 integer here. Reason for that is sometimes when you solve equations, you get negative values. On this equation, you subtract 5 from both sides and you have a negative. Negatives didn't exist in human society for thousands of years, but as we got more complicated, it became necessary. I mean, if someone owes you something, you can reflect that as a negative sign. Their balance with you is negative. Then this wasn't good enough because we want to solve these kinds of equations. 2x plus 5 equals 0. We get values that look like this, negative 5 halves. And now we're dealing with this set, Q. Let's give this a name. Q is the set of all rational numbers. When you say rational numbers, we're not saying numbers you can reason with. We're just saying numbers that you can write as a ratio, P divided by Q. P has to be any integer, positive, negative, even 0. But Q has to be in Z plus. Yeah, go ahead. Square root of 2? It would be. And that's a kind of equation where you'd have x squared plus, let's make it a little bit better, x squared minus 2 equals 0. I didn't want to put a plus there. But that's kind of why we're going to I, the set of irrational numbers. If you wanted to solve this equation, you would say x squared equals a positive 2. Take the square root of both sides and you have x equals square root of 2. But now suddenly that number is really wild. If you look at its decimal expansion, it is never going to stop. It's non-terminating, and it'll never repeat. No matter how many digits you look at, there's no block of digits that suddenly repeats forever. So we call these numbers irrational. The symbol for that is I guess I for irrational. And that's because you're solving equations like you're mentioning, getting a square root of 2 or a square root of 5, positive or negative here. And I should say, there's really 2 answers on this one. Positive or negative root 2. That's a bad-sided example, unless we put both the possible answers on it. So if we take these 2 sets, Q, these are all the nice fractions. I, these are the weird things, irrational numbers like pi, square root of 2, and so on. Put them together, and you have the set we've been working on for pretty much this entire semester, the set of real numbers, which you can write out in interval notation and so on. So we have an entire continuum. You can draw this as a number line, but there is still a huge, huge problem with all this kind of stuff. This is the problem. It's all about equation solving. We needed to solve this equation, so we put in a 0. To solve that equation, we needed negatives. For this one, we needed fractions. For this one, we needed irrational numbers like square root of 2. If you're going to solve that equation, you have a huge, huge problem. The real number system won't give you a solution there. And it's not that it has no solution. It's just that the solution is not a real number. It's not in the set R. So we extend down to C. Finally, what the notes are all about, the set of complex numbers, they're in this form, a set of all numbers of the form a plus bi, where a, b are in R. So it's all about this I for the moment. What is it? Where did it come from? It's coming from this kind of equation. Suppose you're solving x squared minus 1 equals 0. Or like an example, x squared plus 5 equals 0. Let's solve this one on our own right here. Oh, and I want to make one change. Put a plus there. Now it's a nasty equation. You could subtract 1 from both sides and get x squared equals -1. But already that looks like a contradiction because a number times a number always results in positive, not negative. X squared means a number times a number. But that's the thinking in the real number system. Go to the complex number system and we are losing a lot of different things like we're expecting. There's actually no real notion of a negative complex number versus a positive complex number. You can square a complex number and get a negative real number like this one. So what people did historically, hundreds of years ago, was they said, let's solve this thing. We're going to square root it, just like we did up here on this equation. You'll get x equals 2 different versions, root -1 or negative root -1. These are weird looking numbers, so people called them imaginary. They don't exist as real numbers, but they solve our original equation. And we can say, let I equal the square root of -1. Upon doing that, that's how we're getting answers like this one. You subtract 5 from both sides, take the square roots, and those are the answers that you're going to be picking up. So we're not doing as much of equation solving in these notes. They'll come up in chapter 4. It's more about just practicing with that right there as a purpose of what we're doing today. Any questions or comments so far, folks? Yeah, go ahead.
The Q union I is just a different way of writing all the numbers.
Exactly. It's just saying all of your fractions together with all of your irrational numbers like √2 and so on. Other questions so far? Okay, so with all this work, the big question that people had historically in mathematics was, all of these are polynomial equations. And we wondered, if you came up with different polynomial equations, can you find a way to write down an equation with no solution? No solution as a real number, no solution in the complex number system. And that question was answered no by the mathematician Johann Carl Friedrich Gauss. Gauss is one of those legendary mathematicians that just seemed to know about everything that was going on in his field at the time. And this is our major goal that we're trying to drive towards in this course, at least as far as the equation solving goes. The fundamental theorem of algebra says every polynomial equation, like say that one above or more crazy looking ones, this is what a generic polynomial equation would look like. A constant times a variable to the power n, a different constant times another variable to the power of n minus 1, on and so on. There is always going to be a solution within the complex number system. So no matter what, if you write down a polynomial equation, you will have solutions. That's for that reason we don't extend past the complex number system. That's really a system right at the top because it will be the big enough field of numbers to solve even the wildest polynomial equation like this one. So that's what we're dealing with so far. And think of this as an introductory to what we're getting into. And our major takeaway is that's our new object. We'll call that the imaginary unit I, defined to be the square root of -1. And if we take something like a plus bi, this is that's supposed to be an arrow. Let me make a better arrow. When you put a plus bi together, this is a complex number. So our goal, again, is just back to practice working with these kinds of complex numbers. Any questions or comments at the moment? Okay, so we're going to be taking a look at these sorts of equations where we'd ordinarily say no solution. We're going to come up with solutions. And to start out, well, here's the kind of equation we looked at before. X squared equals -1, square root both sides, and you have this as the solution. Or I don't think I wrote down the solution. Let's write it down here. If x squared equals -1, we would square root both sides and get x equals positive or negative square root -1. Then we use that definition right there and re-express the answers as x equals -i or positive I. So those are the two solutions to that equation right there. Essentially the one we did up in the notes, but this one, we already subtracted 1 on both sides. Well, any questions or comments at the moment? Okay, so the big takeaway is really this highlighted yellow. So what we're going to start off is just practice using this new complex number unit and simplify things that look like that, say a square root of a negative number. If you were to deal with this, first, let's put down some formulas we're going to need with square roots. One important formula goes, the square root of a times b is the square root of a times the square root of b. So we'll need that to simplify our equation. Another thing we can say right away is, due to that negative right there, it's going to turn into I root 27. So we factor away the negative, root -1 like this, and just reproduce an I. So if you have a negative in the root, eliminate it, put an I outside, and you're in business. We're simplifying something that would automatically return not a real number in a typical calculator. Any questions at the moment to that stage? Okay, for us, if we want to simplify this even further, it's definitely going to be a good idea. We can call this I root 27 factors as, say, 9 times 3. And this is where I'm going to use this formula. I factored this in a way so we have a perfect square 9. We can put it in one root. We have root 3 that we can't simplify at all. We want the exact answer, and writing it as root 3 is as exact as it gets. Last thing to do is take the root of 9 here, and we get 3i times the root of 3. So the square root of a -27 turns into just this. I was trying to keep my eyes highlighted in blue, so we'll just go with that trick there. Any questions at all, folks, on running through this one? Okay, so let's take a look at it, just a couple more versions. Sounds like it's raining out there. This one has the same kind of thing going on for it. We have a negative inside a square root, so we can immediately take this and re-express it as I root 32 division by root 16. So the denominator is not so bad, right? That's just a 4. But actually, I'm not going to simplify by taking the root of that denominator. The reason is the numerator is not as friendly. It's kind of like simplifying root 27. But 16 does go into 32. Instead of trying to simplify a root like we did in part A, it's better to just combine the roots. So here's the next formula we need to know whenever dealing with square roots, whether or not there's a negative inside of it. If you have the root of a over b, this can also be split. In algebra, if there's a multiplication formula, there's probably a division formula, and it goes root a division by root b. That's what we have right here. We have an a for 32, we have a b for 16. So I'm going to take the right-hand side of this formula and go to the left. If they're split up, you can just recombine them as the big punchline. So this would turn into I root a big square root 32 over 16. Now we're on this left-hand side of the formula. Reason for doing that is 16 will go into 32 twice, and the whole thing turns into I root 2. Just going to kind of order that away so it's not part of the solution. And that's how that one simplifies right there. Essentially, all we did was the negative became I. We divide 16 into 32. It's still in the root, so we have a root 2 as our end answer. Any questions at all, folks, with that second version there? Okay, really kind of doing 3 things at once. Well, 2 things at once, really. We're getting used to I, the complex unit, and we're also discussing weird formulas with square roots that are things we need to be aware of, and things are coming shortly in chapter 4. I think I have another one here. Let's try it out. No, I don't. Well, any questions at all, folks, before we try a different type of problem? Okay, so what we're going to do next is just deal with I itself. Sometimes, for example, you have to simplify an I squared. That actually will come up a lot. And just for the sake of practice, let's simplify all of these. They're just different powers of I, and then suddenly we jump to power 37 because there's going to be a pattern somewhere inside there. First thing I would do to get started with this is, let's recall that I itself is the square root of -1. If you have that down pat, then you can run through each one of these and get some good values in. So for example, for I squared, any volunteers on what this should turn into? It'd be -1. Good call, folks. One way you could write that out is you could say it's I times I. Then you can go over here, make a substitution. You're just saying root -1 times root -1. Then we use the common idea that if you take a root times a root, you should just get the radicand, the thing inside. So the -1 is what emerges on this one. So this on its own is a pretty good formula. Let's use this color to make it shine. I squared is -1. Putting that in a box just as a reminder, it's going to come up quite a lot in these notes. And now we want to try it again. Well, we got a -1 when we did I squared. So what about I cubed? Anyone see what that one ought to be? Yeah, good call. This is just a -I. One way you could write this out if you were to show steps, which you wouldn't have to. If you told me -I, I'm totally happy with that. But if you wanted the steps, here's the one idea. You can factor these kinds of things. If it's I cubed, you can factor it down as I squared times I. The reason for doing that is you look up part A and I squared, that's just a -1. So we can make an immediate substitution right here and get that this is -1 times I, giving a value of -I, like you said. So there's an interesting pattern definitely emerging. I starts off as, by definition, root -1. I squared is -1. I cubed is -I. So how about I power 4? Anyone see what ought to be next? Yeah, absolutely. This one's just going to turn into a positive one altogether. That's an interesting simplification, right? If you see I4 on paper, it looks like some nasty, complicated thing, but it's really, you're dealing with I squared times I squared. So you could factor it first. From the prior part B, from part A, I squared itself turns into a -1. So you can substitute that value in here and here. But now we're dealing with a negative times a negative, and our result comes into +1, as you said. So we start with I squared is -1, I power cubed is I power 4 is 1. But if I power 4 is 1, then on this one, I power 5, let's use the same strategy. You can factor it as I power 4 times I. But then this I power 4, it's literally just a 1. The whole thing turns into I. And now this is essentially a repeating pattern. If you go I, then I squared is -1, I cubed is I power 4, well, that one turned into a 1. I power 5 is I. Then, well, I power 6, it should be next a -1. I power 7, just go down the line, it's -I. I power 8, that ought to be a +1. And this just continues forever. So this is repeating, and we see, say, the period of the repeat is 4. It's a periodic pattern, repeating in this set of 4 right here. You'll just keep on getting those same kind of values every time as you go. So if you want to calculate I to the power 37, 2 good strategies. One is just crank it out, fill out this list until we get to I power 37. Or maybe a better strategy, let's use this as a formula. We have that one, that's our definition. This one's a really big formula. But for handling I power 37, the formula we need here is I to the power 4 is just a 1. We use that, we're in really good shape because then I power 37. Let's see, we can break this into I power, how about 36 times I? Now, why do 36? Well, because this is a power 4, or excuse me, it's a multiple of 4. 9 times 4 gives you the 36. Over here, if I power 4 is 1, then we can say I to the power 4 raised to the power 9, which is I to the power 36. Well, all we're doing is taking 1 right there to the power 9. It's still just a 1 altogether. So back down here, I power 36 turns into a 1, and this whole thing is I. Really kind of a weird problem. But I would say the big takeaway with this is it's good to know that this repeats in a pattern of 4. So it's cyclic with length 4. And also in purple, that's probably even the bigger takeaway with this. I squared itself is -1, and that's a simplification that comes up a lot. Then parts E, well, that's just kind of for fun and just reminding ourselves that it's repeating often. Probably not something we'll be asked a lot. But any questions, folks, on getting through these? Okay, so we started off by saying I is a solution to x squared plus 1 is 0. And now we're getting really far here. We have all sorts of things happening with I. It's a weird, interesting algebraic system on its own right. But our main goal of dealing with these is when we go to solve equations, we get these as numbers occasionally. Even if it's a quadratic, a friendly quadratic like x squared plus x plus 1 equals 0, is going to give you solutions that are these things, the complex numbers. What happens with the complex number is you have a part A here, a part B. They're ordinary real numbers, and we say A is the real part of the complex number, and B is the imaginary part. I'm not fond of that word. It's not imaginary in the sense that it doesn't exist. It exists as a made-up math concept. It really is something that we're working with. We call it imaginary because it goes with the imaginary unit I, right here. And just for the sake of writing this out, I is root -1, just as a reminder. So that's what we mean by a complex number. And pretty much example 3 here is our quiz, just practicing working with those complex numbers. Any questions at the moment? Okay, let's give this a try then. The nice thing about complex numbers is they obey the algebraic system that we're used to in dealing with real numbers. And the reason for that is A and B themselves are ordinary real numbers. The only extra information we need is that I squared is -1 because of the definition in yellow right above. So with those two tools, we're in really great shape. If you were thinking of I as just some other variable x, it wouldn't be harmful in part A. You could rewrite this as 5 plus 6i. We can just drop those parentheses. Here we have to distribute through a negative sign. So this is -3 minus 2i. At this stage, we're just combining like terms. So if that was an x and that was an x, your answer would have looked the same. It's going to be 5 minus 3. This is the real part. So we get a real part of 2. The imaginary part is going to be combining these components here. So we're going to get 4i. And then our work is complete right at that stage. How do folks feel about that one? Not too bad? Awesome. It's kind of an ordinary kind of algebra work, but it gets different on part B. So our goal is to return to this form, where we have the real part of the complex number multiplied by the imaginary part times the imaginary unit I. It could happen that A is 0, and you're just going to write a constant times I. And it could happen that B is 0, and your answer is just, say, a real number. So that might happen down there in the notes, if we recall correctly. But let's give this out a try. Once we write this out, we're simplifying and trying to get into this format, like we did in part A. Well, on this one, the algebraic technique is we'll just FOIL it out, so not too bad. Here, we'll take 1 times 2. Then plus 1 times 7i. So no big change there. Have to love the multiplications by 1. Then we multiply here to here. That's going to be plus 2i. And when you multiply here to here, now I'm going to always put this on the notes just to make the notes readable. I'm going to put plus 7i squared. But if you skipped a step here, that would be appropriate. And anyone know what really goes there if you skipped that step? Good call. That I squared right there pulls in this formula. So if you come up with an I power 2, you're really dealing with a -7 right here. So that's kind of the big trick with getting through these kinds of problems. Part A is not so bad, but if you're multiplying and dividing, that formula will come into play. So now it turns into 2 plus, we can combine these all together as a 9i. But this turns into a -7 because I squared itself became a -1. So finally, we have a -5, the 2 minus 7, plus 9i. Our real part is number -5, and the imaginary part is the +9. So we did it, folks. We got it into that format. Well, it's kind of like ordinary algebra, right? If this was 1 plus x, 2 plus 7x, the steps would look almost identical, except for that, which is circled. Anytime you get the I squared, throw in a -1, and you'll be in great shape. Any questions at the moment with these so far? Okay, the one down below, part C, well, this one is more just kind of extra practice in the middle. It has a negative here and here. So probably the way I'd start this is call this I root 36. If you call this 6i, that's even better, plus I root 25. So this one goes really fast, right? We have perfect squares. The root of the 36 turns into a 6. So we get a 6i here. Square root of 25 is 5, so we get a 5i. Then combine those together, and we get 11i. Now, we didn't necessarily put it in this form exactly, because I don't have a number in front of the 11. You could put 0 plus 11i if you really wanted to, but you don't have to follow the instructions to the letter on that. If you just left your work like this, I'm completely fine with that as well. And we would call this number purely imaginary because it doesn't have the number in front, the real part A, like we did on parts A and part B. We just get the 11i on this one. Does that look right to folks on these so far? Awesome. So we practiced these kinds of things, subtracting complex numbers, adding complex numbers, multiplying them. We'll do another multiplication right here. And these last two, parts C and F, they're the tricky ones. I only asked one on that quiz. I think it's similar to, well, they're both about the same. But before we get to those two, let's take a look at part D. Part D is actually kind of special. But where it comes from is this formula right here. If you take an A plus B times an A minus B, that's a wonderful formula. We've used that a couple times in this class, I believe. If you FOIL this out, the middle terms always cancel, and you get A squared minus B squared. This formula is used in factoring all the time. Sometimes it's used for rationalizing denominators, and it's going to be used in part E and F for dividing complex numbers. It's kind of a surprise. So this formula is sometimes called a difference of squares. And when you form a difference of squares, the only thing that changes is the sign in the middle. We're taking A minus B times A plus B. And so that alone has a name as well. A plus B, A minus B are conjugate. Let me make sure I spell conjugate right. Conjugate pairs. What makes them a pair of conjugates is the sign is different in the middle. So that's kind of what's happening here. We have a negative in the middle, a positive in the middle, but the real part and the imaginary part are completely identical. If you have a pair of conjugates, then multiplying these out is in fact really, really fast. I'll do the full steps and then we'll take a look at their shortcuts when we try this again in part E. So multiplying these out, you do √3 times √3, but that's just going to give you a 3 right back. Does that make sense on that simplification there? Awesome. You can think of that as being a √9, which would reduce to 3. Then we're going to take a √3 times I√2. Both of those have roots, so the √3 and the √2 combine as √3 times 2, giving a √6 altogether. So when we do that multiplication, what I visualize is, well, we know there's going to be an I, here it is. And then the 3 by 2 gives us a √6, like that. Then we just do it again. Here to here, that's almost the same, right? Except it's going to be negative I √6. And last thing that happens is when we multiply here to here, well, we're going to get a negative, then we'll get an I squared. Then √2 times √2 will give us a 2. And that's how it settles after we fully FOIL it all out. That look right to folks so far? Okay, the nice thing about a pair of conjugates when you're dealing with complex numbers is that this cancels. And it's even nicer. That's going to turn into a -1 right there. So there is going to be no imaginary unit I whatsoever. What happens when we multiply two conjugates, even if they were complex numbers to start, we're getting a purely real number this time, as opposed to the purely imaginary number in part C. So let's continue to simplify this. This is 3. In place of that I squared, we're going to put in a -1. Let me highlight that in yellow just to track where that change is. And to me, this is the tricky thing about a formula with I squared. We know it's -1, but suddenly there's extra negative signs there we also have to account for. So this turns into 3 plus 2 for a value of 5. Much like in part C, if all you have is the real part right here and no i's, it's okay to leave your answer in that form. And we would call this thing purely real. As opposed to when here we got to purely imaginary. Yeah, go ahead. Oh, let me take a look at that. I think we did track it. This ×2 came down right here.
It would be 3 plus 1.
Oh, but we have to do these multiplications right here.
3 times 2 should be 6.
Oh, but there wouldn't be a multiplication. The steps here would kind of go like this. Let me put it down to the margin right here. It was 3 minus a -1 times 2. We have to do that multiplication first. So we got 3 minus a -2. Then your negatives, because it's a minus right here, converts to plus. And that's what's getting us down to a 5 on that one. That makes sense for that one? Oh, no worries. Thanks for asking about that one. And again, that's kind of what's tricky about this is a lot of stuff is happening in just one step, right? We're simplifying the I squared. Now we have multiple negatives to account for. It's easy to know exactly what's going on, but still make the tiniest of a mistake on this kind of stuff. Well, any questions or comments at the moment? Okay, so part D was all about conjugate pairs. And the reason we needed all that is now for part E. If we're going to divide complex numbers, recall our goal is to get to this form, A plus BI. What we really need is a conjugate. We have to take the complex number out of that denominator, much like if you were rationalizing a denominator in a different algebra class. So the way this one's going to go is, first thing I would do is be really, really picky about the format of that number. We want our numbers formatted as A plus BI. And there's a really good reason for that. A plus BI has conjugate A minus BI. If I wrote A minus first, I would have said its conjugate is A plus BI. So we just changed the sign in the middle. But what qualifies for the middle is sometimes tricky. Let's take a look at part E and part F simultaneously. Part F is a nasty, nasty question. the number 4i minus 11 should really be written this way. Negative 11 plus 4i has conjugate negative 11 minus 4i. And the reason for that is the sign that we flip is the sign that's attached to the term that involves I itself. If I came first, you're not flipping that sign. If we did, it wouldn't be what we wanted at all. So sometimes we have to fix the format. And that's why this problem is fussing about the a plus bi. It's actually extremely helpful algebraically, especially if you're in part E and F, dividing complex numbers. Well, any questions, folks, before we give this a try? Okay, what I'm going to do is just say it's equal to 10 minus I, 2 minus I. And then here's our trick. Multiply by, let me say a little bit better, multiply top and bottom by the conjugate of the denominator. So suddenly this is all about conjugates at the last part of these notes. To get a conjugate of the denominator, anyone see what it would turn into? Exactly. We take a look at where I is, change its sign, and here's what we're going to get. 2 plus I going here and here. So that's the conjugates right there in blue. At this stage, well, we just have to do 2 sets of complex number multiplications. The one in the denominator is always fast. It has this shortcut right here. You just get the first term squared minus the second term squared. If you fully FOILed it out, that's not too bad either, in all honesty. So let's work this out and see what we're going to get. Multiply the numerators across, we'll have to FOIL. Here to here is going to give us 20. Then it's going to be plus 20i. Then we change gears and distribute the negative I through. Here to here will be minus 2i. Oh, sorry, question first. Oh, yeah, absolutely. Thanks for spotting that. My multiplications have gone completely sideways. That's a 10i right there. Let me fix that number and put in 10i. Good eye on that. Thanks for spotting that 10 there. Other questions so far? Okay, let's go and distribute the next portion. Negative I multiplies through right here, so it's a minus 2i. And when we multiply here to here, it's going to be minus I squared. If you put a plus 1 right there, you've done 2 things at once. That's not a bad thing to do. But I always show this extra step in the notes. That I squared itself is going to turn into a negative 1. So this is negative of negative 1, returning us a positive 1 on the next step. Now down below, well, the formula should be you square the first term. So here it is. 2 times 2 is squaring the first term, giving us a 4. There'll always be a minus in the middle, and then you're going to square here to here. But if we took the extra steps, here's what it would look like. Here's plus 2i. Here to here is minus 2i. And then the last multiplication is here to here. It's indicating we're going to get a negative of something squared. And yeah, we're getting negative of I squared. But once again, that's just turning into a positive 1 as well. The middle terms cancel. And so if you just gave me 4 minus I squared, that's okay as well. It would tell me you're anticipating a difference of squares, and middle terms are just going to cancel when you FOIL through. So now that it's fully FOILed, our goal is to simplify this and get it into the format of a plus bi. Any questions at all to this stage? Okay, we're getting through it, folks. Almost done with the complex numbers. On their next step, let's just say this is 20 plus, this will turn into 8i when we combine those like terms. And this is a negative 1 times another negative 1, giving us a positive 1 right here. I'll highlight that in green because again, that's a tricky business there where I squared turned into -1 itself. Then down in the denominator, same idea. We have a 4 plus, and right here, another positive 1. So we're in good shape. All we're going to do is simplify the numerator, divide by 5 at this stage. So here's how the problem is going to end. It's 21 plus AI divide by 5. Then to get in this format, a plus bi, just divide both terms by 5 and you're in great shape. So it's going to be 21/5. That's the real part, plus 8/5 times I. And the 8/5 of I is the imaginary part right there. We put that as a more real looking 5. Well, we got it, folks. Dividing complex numbers is a little bit irritating, to be completely honest. You have to go into a whole new strategy, multiply by the conjugate, which means you're foiling the numerator and denominator, simplify it down, and that's what your answer is going to look like in the very end. Well, we're just about done with the notes. Today might be a kind of a shorter class, but any questions before we try the next one? Okay, let's give this next one a try. I think the last question on the quiz is pretty similar to either one. Again, the major thing to watch out in part F is the denominator is just in the wrong order to find the actual conjugate. Very first step on part F should be put both the numbers in its standard form. Real part first, minus the imaginary part times I. Do it again in the denominator. The real part's -11, that should come first, plus the imaginary part 4 times I. Now, once we get to this stage, the conjugate is much, much easier to see. We take the sign here, which is positive, convert it to a negative sign, and it'll be -11 minus 4i, -11 minus 4i. So we've got our conjugate in the row. Now, last set of distributions, foiling this all out, and we'll be in business. Any questions at all on the start here? Okay, let's give this a try. So across the numerator, we'll be foiling. Same with the denominator. So parentheses just make it seem like reminding me on what to do on the very next step. One big fraction bar, and here it goes. Multiplying by 10, so this is -110. Here to here will be -40i. Then multiply here to here, that's going to be +33i. And last multiplication. When you multiply here to here, it's -3 times -4, so it's a +12. But it's really a -12, right? Because I also get an I times I for I squared, and we'll use that formula again on the next run. This whole portion right here, how do we highlight before? We used green. This whole portion right here is going to turn into our -1. Does that look right to folks on the numerator? Okay. For the denominator, I did want to show you, I mentioned this once, what a shortcut would look like. So let me know if you like it or hate it. If I were to do this denominator here, because it's automatically a conjugate pair by design, I'm going to get a 4, and I'm going to get the square of that number there, so +1 is what you get each and every time. On this one, we're going to square -11, so it's 121. There will be a plus in the middle. We're going to square 4 for a 16. And where did I go? Well, it was -1. And so the 4i times the -4i became -16i squared. But then that I squared forced the whole thing to become +16 altogether. Because always think of I squared as literally multiplying by -1. That's exactly what you're doing. So that's how the denominator works out really each and every single time. It's kind of nice. But does that look all right to folks taking that shortcut there? Okay, you're welcome to do so as well in your work. But if you feel like just showing the steps, which only takes like 7 extra seconds, is helpful, no harm in just writing it all out sometimes. Well, let's finish off this one to get into the format we need. Across our numerator, we've got, let's take a look, negative 110. That's going to convert into a negative 1. So this is really a negative 12 altogether. All right, negative 110. Here, these are going to combine, giving us minus 7i. And that, like we said, is our negative 12. Then down below, we're going to have 137. It's a huge fraction out of nowhere suddenly. Last steps, combine like terms in the numerator. That's a negative 122 minus 7i. Divide by 137. Lastly, divide by that 137 will be negative 122 137ths. There's our real part. Across here will be minus 7 137ths. That's the imaginary part. And then times I. Well, we got it, folks. That's our complex number. Any questions at all in getting to that end stage there? Okay, we're not going to do a ton of stuff with complex numbers in chapter 4, but they come up enough that it's a good idea to see them, know what they look like, how to add, subtract, multiply, and divide. Mostly though, when we get a complex number, it's going to be a solution to equation. So we'll just state that solution. But any questions at all, folks, on the end of these notes here? Okay, this was a little bit shorter than anticipated. So we're ending like 19 minutes before we were supposed to. But we also got an exam, so I think we are owed ourselves a little bit of a break. If you have questions, I'll be hanging out here. I'll be happy to help out. Then I'll be in room, I forgot, 220 at 4 o'clock across the hall. Well, have a great weekend, folks. If you have questions,